fun.
Yeah. But let's quickly review, how do you do that? Okay, so if I want to do a piecewise function, remember what our strategy is. How do we do that on a graphing calculator? Here's how we structure it. Come on. Okay, so we're just going to put parentheses around for the first piece, right? The first row of the piecewise function represents the first piece of the piecewise function. To get that row into the calculator, that piece, we just do that. We're going to enclose the equation in parentheses, and right next to it, we enclose the domain in parentheses. Now, some people are forgetting this, but then we have to have a plus sign, and then we do the same thing for the next piece. And if we had, many, many pieces, we would just keep doing that. We would link them all together as with plus signs, so that we get a term for each piece. So if I put that in the calculator, that looks like this. Does everybody know how to get these cool fraction templates with the 84s? Okay, so let's look at that. So it's really quick, the way you do that. If I want to get a fraction template, I'm just going to go down to Y3 real quick. Come on. So if I wanted to do for Y3 something like, 2/7 x, you just go alpha F1, enter to get you get a list of templates, and the only one you ever really use is the first one, which is the fraction template. And then I just fill them in. So I just go 2, down arrow, 7, right arrow to get out of the fraction x. Okay, make sense? So that's how you get the fraction. That's kind of nice, because you can visually see then without having to put a bunch of parentheses in there. And otherwise, if you're going to input fractions horizontally on a graphing calculator or a non-graphing calculator, the best way to do that is always to just enclose them in parentheses. So the way I would write that without using the fancy template would just be 2 divided by 7x. Okay? Make sense? But this is probably a better way. I mean, that's visually very nice, isn't it? So you can do that on the calculators. Now, I don't know, I'm not going to spend time on this today, but you don't want to be in any other programs if you don't need to be. And the one I'm thinking of that you'll periodically use is called inequality. That's a useful program. We're going to end up using that quite a bit. We'll use it next chapter a lot, next unit a lot. But when you're not using it, you want to get out of that. If you have questions about how to do that now, come see me and I'll show you. Okay. I don't think it's not going to be a problem. But later on, it will be more of an issue. Okay, so we've got this stuff in there then, and then we put in y2 equals 3. Now remember, when we're going to graph something, we don't just hit graph. The starting point, a good starting place is zoom 6, zoom standard, and this is what we get for this problem. Okay, there's our piecewise function. There's the horizontal line. It's really obvious that there's an intersection there. But there's a big question mark as to whether or not we get an intersection there, isn't there? Right? And the calculator does not do a good job of finding that one. In fact, on this problem, it's really sporadic. Depending on how big the window is or how focused in you are, it'll always find that solution, but it'll hit or miss. It may not find that one. It turns out there is an intersection there, but it may not give it back to you. Okay, and so my point is you have to be very careful. If the intersection is not a place where the function is actually passing across the line, if it's a vertex like this one is, what's really going on there, if we were to look really closely, and we'll do that in a second, is doing something like that, where there's only one point of intersection at the vertex. The calculator is apt to miss those. It just might do that. So how are we going to verify whether there is or is not? Let's talk about that. So this one we can find easily. Right, we know how to do that. We just go second, calc, 5 for intersect. Then is y1 one of the curves? Yeah. Is y2 the other curve? Yeah. Make a guess. Well, that's good enough for that. The first one's so easy to find for the calculator. It's going to go right to it. So that's one answer. One answer is going to be 1.133 rounded to 3 places. Okay, but what about this other guy? If I try to do the same thing, if I go second, calc, 5, enter, enter, and then I make a guess over here. On this scale, the resolution isn't very good, but it looks like that's pretty close to where it should be. If I hit enter, it thinks about it a whole bunch and doesn't find it. It really is there, though. So what do I do? Well, one thing you can do is you can zoom in on that. If you don't know about this little feature, this is a great one. If I go to the zoom menu, the first option, zoom box, that's really cool. If I hit zoom box, it just pops up a little cursor, and I'm going to get to define a window on the screen that's going to, when I hit enter, it's going to expand to the whole screen, right? I'm going to choose a box, and then it'll blow it up to the whole screen size. So if I want to do that, I probably want to do something like go over my left edge. Maybe I'll put, you know, right about there-ish. Go up a little bit. So when I hit enter, it's going to anchor that as the upper left corner for me, or whatever corner I choose. I set it up to be my upper left corner. Now I'm going to drag out. If I go down, if I go down and to the right, it's going to build this window for me. I'll just stop there. How about? Okay, so it's going to build that window. If I hit enter, there's the parabola. Okay. There's the line, but it looks like it. How do you know? I mean, maybe it's just missing it and we're not focused in. You could spend all day zooming in on this thing, and it's going to be really hard to tell by just zooming in whether it's hitting it or not. So we're going to use a different strategy. Let's trace, and let's try to find the x value where it looks like the peak of that first curve is, the one that's curving, so we can see what's the x value that we need to be checking. If I trace along here to the right, well, it looks like I'm starting to go down. My x value is 4.08. If I go back to the left, ooh, that looks like I'm just getting to the top and going down a little bit. So what x value does it look like is going to be the winner, if there is one? So 3 point, but what's that trying to do, probably? Yeah, it's probably 4, isn't it? Right? Does that make sense? There is a way to find out, by the way. I'll just show you a quick trick. If I want to know where the maximum actually is, this is kind of we haven't gotten this far yet, but I could go second, calc, maximum. How about that? If I go maximum, okay, and then do I want it for y1? Yeah, I do. That's the function I'm interested in, right? It wants a left boundary, so I can just trace over to the left of the maximum a little bit. So like right there, hit enter. It wants a right boundary. So we'll go over to the right, so we're past it on the right a little bit. Okay. And then it wants a guess, so I just have to pick a value that's close to the actual maximum. So something like that. Oops, too far. Whoops, slow down. Okay, so enter, and it'll tell me that the maximum is, this is saying 3.99999. What's that really trying to do, though? 4. It's trying to do 4. So the x value is trying to be 4, right? Look at the y value, though. 3. It's 3. At least rounded to 3 places. What is that? 4. That's 4. So look, it really is at y equals 3. Okay? If we use the maximum, it tells us, so then that's a solution, isn't it? That's an intersection. Because the function, if we want to know where is the function equal to 3, well, that's one of them, at x equals 4, right? Now, what if we didn't use, so does that make sense? I'm going to slow down for a second. So the answer is this one and 4, right? 4.000, we just write 4. But if I round that to 3 places, that rounds up to 4, right?
Yeah, right.
Okay, but the point I'm making here, and I know you guys are anxious to get down, but really just focus, hold on for a second and focus on this, because this is important, is how do we find that other solution, right? Because it didn't show up. When we hit intersect, the calculator missed it, and it will occasionally, there's some little, it'll do stuff like that. The calculator is not perfect. It's a great tool, but it's a numerical tool. It's always going to make these big numerical calculations, and sometimes it misses stuff that's hard to find. And so you got to sometimes double check the calculator. Yeah, this is a problem that showed up on someone's test. It could show up on your test. So how do you know? If it's really close like that, well, you could go through and use the maximum feature like we just did, and it tells you that the highest point is at y equals 3, so it's an intersection. Now, what if the highest point had been at 2.995? Then it wouldn't have been an intersection, it would have been below. What if it would have been at like 3.015? Then there would have been 2, because this thing would have been picked up to where it would have actually run into, see what I'm saying, if the maximum was above the line, there would have had to have been 2 intersections there where it crossed through. So there's a lot of stuff we can figure out from that. If you don't use the maximum feature, if you don't use the maximum trick on the calculator, and I was even planning on showing that to you, what we did before when we just traced along this thing, remember, we said, well, it looks like it said x equals 4 is where potentially there's going to be a peak. So then we could just go to the calculator and say second calc value and plug in x equals 4 and see what it spits out. If I plug in 4, enter, look, it gives me back a y value of 3. So it did tell us that when we used the calculator to figure that out, yeah, we do get a y value of 3 when x equals 4, and we don't even need the calculator for that matter. We could even just do this. Really, if all I'm trying to do, you know, you don't have to use the calculator. If you want to get the answer analytically, if that's easier, in this case it might be. If I want to find out what f of 4 is, because 4 was that value that we wanted to try, we can see that's where potentially the value of the function was going to push up to 3, right? I could just plug that in manually. No big deal. If I plug 4 into this thing, clearly it's going to put us down here, right? Yeah. We're going to be on the bottom piece of the function when x equals 4. So if I plug that in, what do I get? Well, that first term is just going to be minus 1/6 times 4 squared. What's that? 16. Okay, so times 16, plus the second term is just 4/3 times 4, plus 1/3. Well, what is negative 1/6 times 16? Negative 16/6, which reduces to negative 8/3, right? Yeah. Plus, what's that? Not 16/3, right? If I multiply, I'm really multiplying by 4 over 1, right? So plus 16/3 plus 1/3. So if I add all those up, I've got common denominator. So negative 8/3 plus 16/3 is plus 1/3. 9/3 is what? 3. Ah, okay, so look at that. We found out, yeah, f of 4 is 3. That means that the function goes through the point x equals 4, y equals 3. We can just do it by hand. We don't even need the calculator. But we verified.
So you'd be guessing.
What's that?
You'd be guessing then, like, because...
How are we guessing?
Are you saying you put the f of 4 in after you figure out that that's 4?
No. If we figured out it's 4 in here, we wouldn't have needed to.
Yeah.
But my point is just that you didn't even need to use the calculator. When we looked at this thing, and we said...
when would you need 4?
Where would I get the 4? Yeah. Oh, that was by tracing along and saying, okay, well, it looks like that peak is going to be...
Okay, so,
right.
So it's kind of a guess, but it's an educated guess.
Right. Yeah.
It was 2.99,
Okay, now this is, once again, I would argue, you know, for you guys, you're likely to go into careers where you're going to just need to know how to do math really well. So for you guys, this is, but even if you weren't going to go into something that was sort of mathematically oriented, this is the kind of thing that you might need to know how to do, because in life, math is 99% of the time outside of math is useful for building models. And I could come up with a million different individual examples, but let's say you are maybe you're working for the National Forest Service, and you're trying to get some data that's predicting how much carbon is stored in trees in Umatilla Forest. Well, you're going to have a bunch of data about the height of a tree as a function of how old it is, like, you know, hundreds of thousands of data points that people go out and collect. You put it into a database, Excel or something, and it spits out through regression some formula. Well, you're going to have to be able to analyze that curve to know, you know, what do we want to maximize, you know, what are we going to do here? Well, you got to make some decisions, big time decisions. Millions of dollars hinge on how you're spending this money to, you know, to make the forest as productive and healthy as possible. So you got to know how to analyze that curve to say, okay, boss, here's what you got to do. go spend $10 million and make this happen. I feel confident that I did the math right. So, I mean, it may not seem feasible now, but I promise you, you guys are all going to be doing stuff like this potentially down the line. Okay? No, you'll be fine. Okay. If you have an absolute value question when we get down there, come up and see me. Yeah. Let's head down.